Here is a very useful machine learning trick that can solve many important problems. Here we give an example of how to use this trick. We use machine learning all the time. Example, YouTube recommends videos for us to watch. Facebook suggests posts based on our past history. And Google Maps can find the best route for us to reach our destinations. And Amazon recommends products based on machine learning. But machine learning needs a ton of data. And what if we don't have so much of data? Here we show how to use machine learning with small data sets. And this is a trick that we discussed at length in a very recent paper in Acta Materiala that has just been published. Machine learning using small data sets is very important. So here is an example. 3D printing or additive manufacturing is very widely used now to make metallic parts. But very often these parts develop cracks and the parts may be rejected because of that. How do we solve this problem using machine learning? Of course, machine learning needs data on the effect of variables. There are many variables that can affect the quality of the parts made by 3D printing. Examples are laser power, beam radius, scanning speed, layer thickness. There are about 12 such variables that affect the quality of the part. So we need the effects of all those 12 variables in our data set in order to use machine learning. So 12 variables. How many data points do we need to represent the effects of 12 variables? If we use a two-factor design of experiments, we will need 2 to the power 12 or 4096 data points. And if we do one experiment daily, that means we will need to do experiments every day for the next 11 years to collect all the data we need to use machine learning to reduce cracks in printed parts. And that's a lot of data, so we must work with fewer data. But how? We are going to show here that adding physics to machine learning reduces the number of variables and therefore the number of data.
We are limited by the amount of data available if we use 12 variables to understand cracking in additive manufacturing. So we must use fewer variables. But how to reduce the number of variables? The number of variables can be reduced if we identify variables that represents the physics of crack formation. Such variables can be derived from a physics-based model of additive manufacturing. The input to this model are the process variables and alloy properties. The outputs are temperature fields, fusion zone geometry, and many other important variables. In the context of cracking susceptibility, such computed variables include cooling rate, temperature gradient to solidification growth rate ratio, ratio of vulnerable time to relaxation time, and solidification stress. These 4 computed variables, along with available data of crack formation, are then used to train a machine learning algorithm to predict cracking susceptibility with exceptional accuracy. Unlike the 12 variables, these 4 variables just need 16 experiments to generate the necessary dataset. But of course, we can generate more than the minimum required data. With the required data using the 4 computed variables, we are one step closer to solving the cracking problem. Using the available sets of raw data and data from a well-tested mechanistic model developed here at Penn State, we derived a cracking susceptibility index that can forecast when cracks may form in a 3D printed part. This cracking susceptibility index includes the four computed variables of solidification stress sigma, ratio of vulnerable and relaxation time beta, temperature gradient to solidification growth rate ratio epsilon, and cooling rate tau. Here, a physics information learning was used to derive the cracking susceptibility index. But it was not based only on the raw data. The cracking susceptibility index varies between 0 and 1, and a critical threshold of 0.5 was able to delineate the cracked and crack-free cases for 102 data. Rigorous testing shows that these predictions are very accurate.
So, the trick of adding physics to machine learning has the potential to solve many important problems. If you need more details about this powerful trick, they are available in this just published Actamate paper. Is there any evidence that this powerful method works for other problems? We found that a common surface defect in additively manufactured parts, known as balling, can be minimized using physics-informed machine learning, and we published our finding in Applied Materials today. Also, you may be interested in the most recent MRS Bulletin news and the GitHub blog that have featured the Actamate paper. Links to these articles are given in the description of this video. There are three unmistakable impacts of using this trick. First, it can guide engineers in process parameters and material selection for an application. Second, it provides a new pathway to print defect-free parts without expensive and time-consuming trial and error. And finally, this trick is solely based on scientific principles and does not need any expensive equipment. If you know of other engineering problems that can be solved by using this machine learning trick, please let us know in the comment.